Okay, in section 1.1, and let me say before I forget, I have in the syllabus section 1.2, and then I have homework see below for 1.2. It's actually section 1.3. I'm skipping section 1.2. The old book to the new book, same section. Old book is 1.2. This 10th edition is 1.3. So um, I did correct it in my notes here, and I will also update that in Blackboard for you as well. So in section 1.1, just a few problems here where they give you a solution, and then they want you to simply verify that that indeed is the solution. Later on, as we go, this would be a guideline for you that when you solve a differential equation, take that solution that you found and go back and check it into that original equation to make sure that everything checks out. Almost like in algebra where you get an answer, you go back and just plug that answer in to make sure the left side is equal to the right side. In doing that, it is really good because you will know before you leave that particular problem whether or not it's right or wrong. Okay? Again, we said on before that a differential equation is any equation with a derivative or a differential in it. So we take this problem and assuming here that what they give us is the solution, can we verify? Well, if y is equal to this implies that y prime is equal to negative 1/2 times e to the negative x over 2. So we plug that in for y prime. So we have 2 times negative 1/2 times e to the negative x over 2 plus y. Y is given to be e to the negative x over 2. That's equal to, just keep on working that out. So we just simplify. We get negative e to the negative x over 2 plus e to the negative x over 2. And indeed, that's 0. So secondly, take this problem. So if y is this, so y prime would be negative 6 over 5 times negative 20 times e to the negative 20t. So we simplify that, the negatives go out, and so we have 20 divided by 5 is 4. So here we get 24 times e to the negative 20t. So obviously y prime is the same as dy over dx, not dt. Okay, so we have y prime, which is here the 24 e to the negative 20t plus 20 times y, and y would be 6 over 5 minus 6 over 5 times e to the negative 20t. So this is 24 e to the negative 20t. Distribute the 20. So we have plus 24 minus 24 times e to the negative 20t. And so the 24 e to the negative 20t cancels out with this opposite. And so we're left with 24, and that's what the original differential equation said it ought to be. Right? Then this problem here, it's the last one that I do here, save the other one for you. So y prime is equal to 25 plus y squared. Y is given to be 5 tangent 5x. So y prime would be 5 times, the derivative off the 5x would give us a 5. So that's 5 times 5 is 25. And the derivative of tangent is secant square 5x. So now is y prime equal to 25 plus y squared? Let's see. So y prime would be 25 secant square 5x. Is that equal to, question mark, 25 plus y is 5 tangent 5x. So this would be 25 tangent squared 5x. And if you just divide through by a 25, we get a trig identity. So this is secant square 5x is equal to 1 plus tangent square 5x which is a trig identity, right? Now, you recall that cosine square x is equal to, cosine square x plus sine square x is equal to 1. And so if we divide through by cosine square x, so this implies that we have cosine square x divided by cosine square x plus sine square x divided by cosine square x is equal to 1 over cosine square x. So that implies that we have 1 plus tangent square x is equal to secant square x. And we all knew that. Okay. Good. Any questions? All right, the two other sets of problems here considers the same idea. If we give you a solution, here we give you a solution type. We give you a solution type of a differential equation. Can you verify that? Now, as we go through this course, we will learn how to originate the solution. And so here we just give the solution, and we ask the question, can you check to see if this solution is indeed the solution for this particular differential equation? Later on, we'll actually produce, such solutions, whether they be exponential or polynomial type, which would be somewhat of a foundation for differential equations. So here, for this problem, it says, find values of m so that the values of the function y equal to e to the mx is a solution. Really, it's a solution type of the given differential equation. We say here that these particular differential equations, their solutions are exponential. When we get to that particular chapter, chapter 4, we will show why the solutions are exponential and be able to find them directly. So here we assume the solution type is of the form y equal to e to the mx, which implies then that y prime would be e to the mx times the derivative of mx, which is just here, m is a constant, which is just m times e to the mx. We only have one derivative, so we stop there. So y prime plus 2y equal to 0 from the problem implies, this is y prime, this is m times e to the mx plus 2 times e to the mx is equal to 0. So looking at this equation here, notice that e to the mx is common, so we factor out e to the mx. So we say here that this implies that e to the mx times what's left, m plus 2 equal to 0. This implies by the product property for 0 that if there are quantities multiplied together equal to 0, then at least, bless you, at least one of those items in the product must be 0. So here, either e to the mx is 0 or m plus 2 is equal to 0. So this implies that e to the mx is equal to 0, or, and it could be or, it could be and. Either one is 0 or they both could be 0. M plus 2 is equal to 0. Well, the problem with e to the mx is that e being a fixed number, e to the mx is never 0. So here, e to the mx is not equal to 0 for all x, right? So m is equal to -2, right, from this guy right here. So that's the value for m. And later on, we'll use that to be able to find solutions to differential equations of this form. The next one, this guy has a second derivative in it, so here we have, well, the assumption is that y is equal to e to the mx so here y prime is m times e to the mx, and y double prime would be m times m, or m squared, times e to the mx. So we just go and just substitute those values into the equation. So y double prime would be m squared times e to the mx minus 5 times y prime. That's going to be m times e to the mx. I guess it would help if I could write better, right? Yeah. Okay, and plus 6 times y, that's 6 times e to the mx is equal to 0. Again, factor out the common term e to the mx, solve for m. So we have e to the mx times brackets m squared minus 5m plus 6 equal to 0. So this implies then that the m squared minus 5x plus 6 is 0. We can factor that. So with m minus 3 and m minus 2 equal to 0. So m equals to 3 and m equals to 2. And so here, the question was, can you find the suitable m, right? So that's all we're looking for. Find values of m. Yes, ma'am. Now, let me give you a pre-warning so that when we get to that chapter, which will be from now until chapter 4, which would seem like a lifetime by the time we get there. But looking at this particular, or these types of differential equations, if you look at them, you know that they are linear. how we define what linearity means for a differential equation, that the dependent variable, which for us for most times would be y, that its power is 1, and its derivative, dy with dx, its power is always 1. It could be the second derivative. That's not the power, it's the order. But if you notice these three problems, this guy right there, right, this one, and then this guy, if you look at how they're strung out, look at the coefficients. The coefficients are numbers, right? The coefficients are numbers. That means something. Here, when the coefficients here are constants, then the solution type is of a certain form, and we'll show that in chapter 4. I'll go ahead and tell you, and that's what these problems are trying to beg. The solution types for differential equation that's linear, and the so-called coefficients are constant terms. The solution type is always exponential, e to some mx. Now, which is different now from the second type. Here it says find values of m so that the values of the function y equal to x to the m is a solution type of the given differential equation. Here, y equal to x to the m is not exponential in the form of the exponential order of e, the base e to some power. Here, these guys, the solutions would be polynomial in type. Why is that? Now, look at this first problem here. Okay, you got the y double prime, you got the y prime. This next problem, you got y double prime, you got y prime, you got y. But look at the coefficients. The coefficients here is x. That's 2. 2 is a constant, but here I got an x there. Look at the coefficients down here. X squared, right? X, right? Well, so these so-called coefficients are not constant terms. They're polynomial in nature. So hence the solution type is also in polynomial form as well. And again, we'll talk about how to do all of that in chapter 4, but they do give problems like this in chapter 1, just to kind of give you an idea of how a differential equation looks like. If you're given a solution, can you verify to make sure that that solution is indeed the solution for that particular equation? So here, y is equal to x to the m. So again, we assume y equal to x to the m is a solution type. So then y prime is, what's the derivative of x to the m? Okay, all right, that's good. That last one, whatever you said, right? Is m times x to the m minus 1. Yeah, right. Well, we have a second derivative here, so we have to find y double prime. So that's m times m minus 1 times x to the m minus 1, which is x to the m minus 2. So we're going to replace the y double prime with this expression here, replace the y prime with this expression there. So we have x times y double prime. So that's going to be times m minus 1 times x to the m minus 2 plus 2 times y prime. Y prime is m times x to the m minus 1 equal to 0. We simplify that. So this is, yes, m times m minus 1 times x to the m minus 1 plus 2 times m times x to the m minus 1, right? This is x to the first power times x to the m minus 2 becomes x to the m minus 1. Right? That's equal to 0. Now the common term that I see is x to the m minus 1. So we factor out x to the m minus 1, and we have left m times m minus 1 plus 2m equal to 0. Here we say assume the solution is on the interval the open interval from 0 to positive infinity. It's on the interval from 0 to positive infinity. Well, this would imply then that x to the m minus 1 is not equal to 0. Because from there you would just get x equal to 0, but if I assume that the solution is on the open interval from 0 to positive infinity, that means that we're not including 0. So from this product, this term times this term, right? Well, if this is not 0, well, this guy has to be 0 in order to get equal to 0 over there, right? So 0 times some number, some term, gives us 0. So here we have the m times m minus 1 plus 2m equal to 0. Simplify that. This implies that you have m squared minus m plus 2m. Just simplify that. That's m squared plus m equal to 0. So we do some factoring. This is m times m plus 1 equals to 0. So here m equals to 0 and m plus 1 equal to 0. That is m equals to negative 1. So the two values that you want for m would be 0 and negative 1. Okay? Any questions there? It'll be the same. I don't think it'll save any time. Yeah, I think the work involved there will be about the same. Yes, ma'am. Okay. All righty. Any questions in section 1.1? Well, let me conclude with 1.1 and then we'll look at 1.2.